In this video, I'm going to show you how to apply exponential equations or models to word problems that could be a little bit harder than the last video that I've done. So sometimes the a or the p in the equation that I've discussed might be unknown. So let's read this question. Health officials found traces of radium F, just the name of some substance, beneath a local library. After 69 days, they observed that a certain amount of the substance decayed to 1/√2 of its original mass. We're not told original mass, notice that. Determine the half-life of radium F. So you don't know the half-life either. So let's start by doing let statements. Our independent variable here would be number of days, and dependent variable will be the mass itself. So we don't know other parts like the original mass, we don't know half-life, but in terms of x and y, let's use dependent y and independent x. So independent usually is time. So I think it's best to create I'm going to show you two versions of it. So I like to create it with a table to explain it. We don't know what the original mass is, so I'm going to use capital A to represent this original mass. And that's at time 0 because it is in the beginning. Then we're told in 69 days that we have now 1/√2 of, so the word of just means to multiply, right? So we have 1/√2 multiplied with A. That's not the only way you could have set up the equation. You could have said, well, because we know the fact that there is a half-life in the question, we could say that the output A becomes half of this A, but how long does it take to do so is some unknown value that we can call P for the period of half-life. So I'm going to show you two ways to do this, so using that or that. So using the first table, we can say that the change in x went up by 69, and the ratio here is a multiple of 1/√2. So that would be our b, and this will be our p. So you can go right ahead and create an equation. The initial value goes here, our ratio goes here, and then x over the differences in x. So that's one setup. If you went with this route, you could say, well, the ratio here is a multiplication by a half, and how long does it take to do so is some unknown quantity p. So in this situation, the equation could look like that. Initial value a, the ratio is 1/2, and then the denominator is unknown p. That's okay. So the important fact is I would like you to know that the denominator underneath the x in the exponent, that's interconnected with the base that you're recording. So this base here corresponds to how long did it take for that base to get cut by this fraction, whereas in this situation we have the base corresponding to the half. How long does it take for something to get halved? Anyways, let's get to actually doing this question. So to create this equation, we have used this point right here, 69, and this value right here for the base, but we haven't used the half of a. So what we can do is say if a, initial value, becomes half, then the x will be the actual half-life p itself. Whereas in this setup, we have not used the value 69 days, and the output would be 1/√2a. This is actually the usual way I would set up this question. I would say, okay, if I see the word half-life, I will put in 1/2 as the base and proceed from there. So if you were to solve these questions, you'll notice actually that this will end up being the same solution regardless of how you set up. So let's do this on the top. So this first one over here, I remove the a's because if you divide both sides by a disappears. So if you were thinking, wait a minute, we have too many unknowns, it actually would not matter what that initial original mass was, because they are irrelevant when we start to solve. So we have 1/2 is equal to this base. And for us to solve this exponential, we need the bases to be identical. So 1/2 is the same thing as 2 with exponent of -1. Changing this to a base of 2 will make it to be with an extra exponent of -1/2. Why negative? Because we moved it upstairs. And why 1/2? Because that's a square root. Now that the bases are the same, we can ignore the bases and match the exponents. So that exponent -1 has to equal to this whole exponent with multiplication. Remember, power of a power. So if you multiply them, you'll have -p over 138. And then when you solve this equation, you'll get a period of 138. That's using this first version. Or you could use this second version. Again, before you proceed to simplify it, divide both sides by a, so that eliminates it. Then rewrite everything with a base of 2. So this 2, we need to bring it upstairs, so that's the negative. The square root becomes 1/2. This 2, make it upstairs, so that's a negative exponent. Once the bases match, you can ignore them and say the exponents have to make them equal to each other to solve this equation. You still get the same result. And so, therefore, statement, we wanted to know how long does it take for the substance to become half. So that's this P right here, and it takes 138 days. This question I would like you to try. So you can pause the video after I read the question and then unpause to see my solution. One substance loses 10% of its mass every so often. So we don't know how long it takes. So again, we don't know that P. How long does it take for it to cut by 10%? We're going to find this period P of loss if we're told in 50 days the amount is halved. So it's very similar to the previous question. So pause the video right now and then unpause when you're ready. So I'm going to assume that you have done that. So here's my solution. Very quickly, you could set it up either this way or this way, as I've discussed before. Here, the P represents this unknown, is the period at which the 10% is being lost. This 10% is incorporated into this 0.90, because 1 subtract 10% is 0.90. So that P relates to this 0.90. And here, we've used 50, because we know it takes 50 days to get the amount to be halved. So in this situation, these two correspond together. And then the X is the amount of days that we want to get 90% of A. So the numerator of the exponent matches to this output. So input and output go together. And then the denominator and the base, they're related to each other. So I'll repeat it over here. The numerator, input 50, corresponds to something being halved. So that corresponds together. And then the denominator corresponds to the base itself. Regardless how you solve this, you can solve it all the way on your own. You can check to see that you should have 7.6 days to get 10% loss. Here's another question that you should try on your own as well. We're told population in 2019 is 7,000 people. And in 2000, let's say it was 500 people. The question is, what is the doubling period of growth? So because it's years, I think it's best to put in, let X be 0 for the year 2000, so you don't have to work with inputs being really large. And at this point in time, pause the video, do the question, and then unpause when you're ready. Okay, I'm going to assume that you have done that. I've done this by creating a table again. So at year 0, which represents 2000, we have 500 people. And then we're told in 2019 we have 7,000. So 19 years from the year 0, we have 7,000. the question is, what is the doubling period? So what does it mean doubling? So we want to double 500 and get 1,000, but we don't know how long does it take to do so. And that our goal is to find this number x for it to get to this 1,000 amount. So you can set it up by saying the initial value would be 500. Then you could say that there's a 14 here. Why 14? 14, remember how I said the base and the denominator, they're related to each other? So where did I get the 14? Well, I'm using the change in x of 19. So if I'm using these two values here, that means I'm going to do a ratio between 7,000 and 500. So if you divide 7,000 by 500, you'll get this 14. And then the only thing left is to find out what is x if y is 1,000. And so when you do that, you will solve it and get the result. That's not the only way to set it up. You could have set it up in this way. You could have said that we don't know the doubling period. So here's the 2 for doubling. And so this 2 relates to this unknown period of p. And then we can plug in the point 19 and 7,000 as our input x and output 7,000 and solve that. Whichever way you do this, you will get 5 as a result. So you would say it takes 5 years for this population to double. So doubling period is 5 years. Another complication that I wanted to discuss is there are certain questions that will actually have a horizontal asymptote that is not a 0. And in that situation, you cannot assume that the initial value that you record is going to be your A, because the horizontal shift up or down, it's going to mess things up. So let's read this question. A sunflower plant growth eventually stops around 2 meters of height. As it grows, you measure the following data. Initial measure was 50 centimeters, and then in a month you measure it again, and you have 120 centimeters. Create a model for this. So because there's going to be a leveling off of height at 2 meters, we're going to say that this is our horizontal asymptote. And the initial measure of 50, do not say A is 50 right now. That's a common mistake. Let's set it up. Instead, by using the concepts that I've talked about previously, in general, if we have this formula with the plus C that's not going to be 0, then what you want to utilize is the fact that there's y-intercept that's going to be always equivalent to A plus C. I'll repeat again where this A plus C comes from. To find the y-intercept, you plug in 0 for the x. So imagine 0 is over here. So any base to power 0 is just 1. And so we'll have just A times 1 plus C, which is A plus C. And so to find A, it's not going to be your initial anymore, because it's going to be your y-intercept minus the C if you rearrange this equation. So don't make an assumption that A is initial in this situation. So if we understand that, let's start with let statements. Let x be number of months, because it talks about then in a month you measure. So we could say the independent variable is to do with months. Let y be the height in centimeters, because we're measuring the height here, we can say it's in centimeters. Create some table to help you figure this out. At times 0 we have 50. We're told that initial. We're told that in 1 month, so 1 month, we have 120. And then we don't know any points, but we do know eventually a horizontal asymptote will be 200. Why 200? Because 2 meters is equivalent to 200 centimeters. So we have a horizontal asymptote, which is not 0. We have it to be at 200. We don't know what B is. But we do know that we can use the denominator in our function. We could just say it's going to count by ones because we have 0 to 1. So we can use P as 1. We do know the y-intercept itself at 0, we're given 50 here. So we can use this fact and the fact that we have the 200 for our horizontal asymptote to solve for the A. Then we can create the equation with the unknown value B. So we still don't know what that B is. That's okay. we have an extra point we haven't used to plug in 1 as the x, and so 1 as x and 120 as the y. That will allow us to find the b. We're going to subtract 200 from both sides, and then divide both sides by negative 150, and we get b is some sort of fraction here. So here's the model. You'll have a b to the x over 1, which you don't have to record, plus 200. So one more question, which you will try. So I'll read it, and then you'll pause to begin it. So again, this is a question where there is a horizontal asymptote. It says, you buy a hot chocolate with unknown temperature. It cools down at a rate of 2% every 5 minutes. You measure the temperature 10 minutes after you buy it, and it measures at 70 degrees Celsius. What was the initial temperature if the room temperature is 20 degrees Celsius? So pause the video right now, and then unpause when you're done. I'm going to assume that you have done so. Here's my solution. We have the rate here is 2%, so please do not say 0.02 is the b. You have to subtract 1 minus 0.02 because it's cooling down, so the temperature is going to go down by this 2%. So b is going to be 1 minus 2%. And it says this percentage is happening every 5 minutes, so that is the period at which this decay is occurring at. Then you can create a table. I didn't do my let statements, but this is kind of my let statement. Minutes represents my x, degrees Celsius is my y. We don't know initial temperature. At 0, we don't know what that is. Okay, it says what is the initial temperature, so we don't know that. But we do know that, what are we told? We're told 10 minutes after you buy it, so here it is, 10 minutes after you buy it, the temperature is 70 degrees Celsius. And we know that as you leave the hot chocolate in a room, it's going to level off to the room temperature. So the leveling off horizontal asymptote number will be the 20 degrees Celsius of the room temperature. Another thing that we figured out up here is that the base is 1 minus 0.02. So the ratio here, even though we don't know what the starting value is, we know that this ratio is 0.98, and that 0.98 is every 5. So I inserted a little 5 here to indicate from 0 to 5 is going to multiply by 0.98, so it's going to decay a little bit. And then from 5 to 10 minutes is going to decay by 2% again, and so on. So based on this table, we can say that the C is 20, that's our horizontal asymptote. B is 0.98, that's our decay rate, decay factor. Watch that I didn't say rate because it's not rate. Rate was 2%, okay? And then P is how long does it take to lose 2%, which was 5. You should put everything that you figured out into the equation. The only thing we do not know is A. So just use another point. So we haven't used in this setup the 70 or the 10. So plug in 10 as the x, 70 as the y, and simplify this. Simplify the exponent first. 10 divided by 5 is 2. Subtract 2 from both sides, or that shouldn't be 2, that should be 20. So pretend that was a 20. 70 minus 20 is 50. I apologize for that, it got erased. Then do the exponent, that gives you this, and then divide both sides by that number, you get 52. Well, here's my 0. Just got captured with the next click. Okay, so then you create your model. You have everything that you need for the model. X and Y are unknowns for the model, and you're ready now to solve for the question. The question is find the initial temperature. Initial temperature means we need X to be 0 to find what is the output. And so we plug in 0. Anything to power 0 is just 1. You add, after you multiply by 1, you get 72. And so that's it.